Hello everyone. So welcome to our video lecture. In our last class we have studied about RS configuration in various type of compounds like Wedge-Dash formula or Fisher projections. We studied about pseudo-chiral center. Okay, so now let's understand some important points about Fisher projection. Okay, so Fisher projection, when we say, it has been given by one scientist. His name was Fisher. So Mr. Fisher made this projection formula Fisher, which says that he placed the groups in perpendicular lines. Okay, means one will be horizontal line and one will be vertical line. And he said that the horizontal line groups or horizontal part represents the molecules or groups or atoms towards the viewer, and the vertical line represents away from the viewer. That's why we say that horizontal line will be wedge position and vertical line will be dash position. Okay, so this is one part, but there are certain important points or characteristics when we draw these structures. Okay, so let's see these points. Important features of Fisher projection. See, first point is Fisher projection must not be lifted over above the plane of paper, we can say. Means if you lift and rotate, revert, okay, lift and place on next opposite side, Fisher projection must not be lifted over above the plane of paper and placed reversibly. Means you just made it reverse order. Okay, such lifting over gives enantiomer. Okay, let me tell you this with an example. Suppose I say fluorine, chlorine, bromine and iodine. Okay, so friends, in this I am telling, if you lift this and turn over, means reverse, okay, means turn over. So if I lift, suppose I am telling I am catching this fluorine, this part to be lifted and turn over, so what you will get? This part and this part will be same, but you lift this part to this part, so bromine will come here and chlorine will come here. Definitely, if you observe these two, they are mirror image of each other, means they are enantiomers. Okay, that's what we are telling here. Such lifting over gives enantiomer when turned. Okay, so if you lift one part above the plane of paper, suppose I am telling this plane as plane of paper plane, okay, or board plane, in the plane, so above lifted and turn over reversibly, means reverting it, then what you will get? You will get enantiomer. Clear? You can see simply that pull towards yourself, lift and turn. See, both are mirror image. Okay, now if I say about RS, see, we have understood all the cases. We have studied enantiomer, we have studied RS configuration, so we can check here easily on all the ways. From iodine to bromine, it is anti-clockwise S. From iodine to bromine, it is clockwise, it is R. You can say both are enantiomers. So I think this point is clear. This was your first point. Second feature, Fisher projection can be rotated in the plane of paper about 180 degree across the chiral center, and it gives identical compound. Now what this rule says, Fisher projection can be rotated in the plane of paper, means you have not to lift now, you just rotate it about 180 degree. Means if the compound is like this, you just rotate it like this, okay, across the center. Which center? Across the chiral center, okay, and it gives identical. Let's say this: fluorine, chlorine, bromine, iodine. So suppose I am holding this fluorine and bromine here, and if I rotate this page, suppose it is a page, and if I rotate like this in any of the direction, okay, so if I say I am rotating this part, okay, so this will come this side, this will go this side, I am rotating like this. So what you will get? You will get this bromine upside and this fluorine downside. At the same time, when you rotate like this, when fluorine comes this side, okay, in that time this iodine will come here and this chlorine will come here, because when you rotate this entire plane, suppose it is a page, okay, in this page I have written this molecule. So if I hold the page and if I just rotate the page, I can see this chlorine and iodine will also interchange. No, this iodine comes here 180 degree and this comes here. Simple. Okay, now let's see whether it is identical or enantiomer. Let's check. We have both the options to check, either RS configuration or check by even and odd interchange. First of all, check it by RS configuration. Here iodine towards bromine, so it is your this is simply clockwise, so configuration is R. Here if I say iodine to bromine, fluorine here, here also fluorine here, so it is your clockwise R. So you can simply see both the compounds are having same configuration, so identical. Means if you rotate the Fisher projection across any chiral center to 180 degree in the plane of paper, means in this plane only, you will get identical molecule. Clear? Now checking by even or odd interchange. See what I have done: iodine chlorine 1 interchange and fluorine bromine 1 interchange, so it is having 2 interchange. Clear to everyone? Okay. So let me tell you third possibility. Rule number 3. Fisher projection can be rotated in plane of paper about 90 degree across the chiral center, but it gives enantiomer. Okay, so if you rotate that same molecule just a 90 degree in the plane of paper, you will get enantiomer. Let's check it. See, every time I am using this simplest example, so you can correlate fluorine, chlorine, bromine and iodine. Okay, now in this plane of paper only, if I rotate, you may rotate clockwise or anti-clockwise, that is your wish. Now I am just telling, rotate it clockwise 90 degree. Rotated 90 degree in the plane clockwise. Okay, what you are going to get? See, this fluorine will come here, this iodine will come here, bromine will come here, and chlorine this side. So fluorine, iodine here, bromine here, and chlorine here. Okay, iodine comes here, this bromine comes here, chlorine comes here, and fluorine comes here. Clear? Just rotate it 90 degree. Okay, now let's check it whether it is identical or it is enantiomer. So if I say this one, iodine to bromine, it is clockwise, and fluorine here, so this is having R configuration. Okay, now check this one, iodine to bromine, it is clockwise, but now fluorine is here, so it is having S configuration. So you can see this compound is R configuration and S configuration, so they are enantiomer of each other. Okay, now let me tell you in terms of odd and even interchange. If you have to find the same compound by odd or even interchange, see, I have to make this compound like this. Okay, means I am changing in even or odd interchange in that compound. So check, we are having bromine here, so just do one thing, first of all make bromine here, one interchange, iodine will come here, so first interchange bromine will be in this position, done. Now iodine comes here. Now we have to make chlorine here, so iodine goes there, second interchange. Now fluorine here, third interchange. So total 3 interchanges required to get the same compound, and odd interchange gives you enantiomer. Clear? So this is your third feature. Point number 4. In Fisher projection, if we fix any group or atom across any chiral center and rotate remaining 3 groups or atoms clockwise or anti-clockwise simultaneously, we will get identical compound. Okay, let's see this with an example. Suppose this is fluorine, chlorine, bromine and iodine. Now check the rule. Rule says in Fisher projection, if we fix any group or atom, let's fix. Fixed means you are freezing this part, freeze now across any chiral center. Okay, and rotate remaining 3 groups. These 3 groups or atoms we are rotating clockwise or anti-clockwise. So I will check by both cases. Okay, both clockwise and anti-clockwise. So if I rotate this part clockwise, means this side. Okay, so iodine will come here, bromine comes here, chlorine comes here. What you will get? Clockwise. You are going to get same. Fluorine was fixed, iodine comes here, bromine comes this side and chlorine comes this side. Okay, what I have done, I am representing here this and this goes here. See, this is simply your clockwise rotation. Okay, freezing one part, rotate clockwise once, simultaneous. Iodine here, bromine here, chlorine here. Now check whether you get identical compound or not. So you can simply see this iodine towards bromine, clockwise rotation, it is having R configuration, and fluorine on vertical, so it is R. Now check iodine towards bromine, clockwise, and fluorine here, so it is also R configuration. So you can simply say these two are identical. So in clockwise rotation, I am sure it is identical. Now let's see anti-clockwise. Okay, so if I say anti-clockwise, what will happen? See, fluorine was fixed. Okay, now anti-clockwise means this side, means iodine goes this side, iodine here, Okay, now if I goes this, chlorine will come here and bromine comes here. Clear to all of you? Now check the configuration of this part also. If it comes same, then it is identical. So on anti-clockwise, anti-clockwise, iodine comes here, chlorine here and bromine here. Okay, check RS. Iodine towards bromine, clockwise it is having R, because fluorine on vertical only, so it is having R configuration, it is also having R configuration. Now you can check simply here. Iodine towards bromine, clockwise it is also having R configuration, so all three are same. So you can see that in Fisher projection, if you fix one part and rotate the remaining part in clockwise or anti-clockwise simultaneously, then you will get identical. Why it is happening? Let me clear you. If you are doing such thing, you are actually doing even interchange. Okay, so when you make even interchange, you will get identical compound. So I think everyone is clear through these 4 rules. Okay, so let's continue. Okay, so dear students, in these 3 compounds you have to check the relationship. They may be identical, or they may be homologous, or they may be enantiomer. Okay, let's check it. If I see this compound, see here I am using all the concepts studied till date. If I see this compound is having plane of symmetry. Okay, so it is optically inactive. Okay, now if I check RS configuration here, this one will be having 1, 2 this side, clockwise, reverse, anti-clockwise, S. Now this one 1, 2, anti-clockwise, reverse, clockwise, this is SR. Now check this one. This compound is not having POS, not COS, optically active. Now configuration here, 1, 2 this side, clockwise, R, reverse, S, because hydrogen in here, 1, 2, clockwise, reverse, S. Now see, if I check this one, this is 1, 2, 3, 4, 2, 3 dibromobutane. This is also 2, 3 dibromobutane. Now check this one, 1, from this bromine, anti-clockwise, so reverse clock, R, and this anti-reverse clock, so it is having RR configuration. Now you can see this is also 2, 3 dibromobutane. So we can understand the molecular formula as well as connectivity, means the structure part of these 3 are same. So these 3 are obviously, it's about stereoisomerism now. So this is POS, optically inactive, optically active. This is also optically active. Okay. Now simply you can observe that compound 2 and 3 are actually mirror image of each other. As we know, when you will place mirror here, this bromine comes this side and this bromine comes this side. This is the mirror image. By configuration also, it is having SS, 2S, 3S. It is having 2R, 3R. Simple. So they bear mirror image relationships. So I can say 2 and 3 enantiomers. Okay, the relation between 2 and 3 is enantiomers. But what about the relation between 1 and 2 or relation between 1 and 3? Okay, so here we have to understand one more concept. See, if I observe compound number 1 and 2, they are neither mirror image of each other and they are neither superposable to each other. Okay, so they are non-superimposable and non-mirror image. So such compounds are called as diastereomers. Okay, so let's study it in detail. Diastereomers. Now what are diastereomers? First point, compounds which are not mirror images of each other and also non-superposable are called diastereoisomers or diastereomers. Okay, both terms are used. Clear? So compounds which are not mirror images of each other, they must not be mirror image to each other and also non-superposable, means all the atoms of this and this must not coincide with each other, because if they coincide they will be identical, right? So these two conditions, neither mirror image nor superposable. In enantiomer it was mirror image but non-superposable. In diastereomer neither mirror image nor superposable. Second point, see, this is one of the most important point. They may be optically active or inactive. For diastereomers it is not compulsory that the compound will be optically active. Okay, for enantiomers it is mandatory, but for diastereomers it is not compulsory. Clear? Now, their physical properties are different. Physical properties as we have discussed for enantiomers, like boiling point, melting point, refractive index, density. So for diastereomers physical properties are different. Okay, clear? Now if I simply say about chemical properties, as the compound will be almost same, molecular formula will be same. See, for two different compounds which are not at all isomer, I cannot say diastereomerism or diastereomer. For a compound having same molecular formula, okay, same structural formula, I will use this term. Clear? So chemical properties are almost the same, not 100% same. Rate of reaction may differ and all such cases. Clear? Now I am giving you one of the best example to understand diastereomer. Geometrical isomers are diastereomers. Okay, so diastereomers are actually stereoisomers which are neither mirror image nor superposable. So best example is geometrical isomers. Let's see with the example. See, this is cis 2 butene and this is trans 2 butene. Okay, now if I see these two compounds, obviously their stability, their boiling point, melting point, these properties are different. Okay, we have discussed this part also in geometrical isomerism. But if I say the relation between these two, then I can simply say the relation will be what? These two are neither mirror image of each other, and also they cannot superimpose each other. So they are diastereomers. Clear to everyone? Okay. Racemic mixture. Now let's understand one more concept. Racemic mixture. What is this? See what happens if we are having one compound which is optically active, okay, and we have drawn its mirror image also. So if we see, suppose this compound number 1 rotates the plane polarized light in any angle theta, okay, so this compound 2 will also rotate the plane polarized light in angle theta only, but the direction of this is suppose clockwise, so this will be anti-clockwise. So if I take the equimolar mixture of these two enantiomers, then what will happen? The net rotation when light passes through this mixture will be 0. Why? This is rotating in theta clockwise, then light comes here, theta anti-clockwise, net result will be 0. Means from here compound light is passed PPL from these two compounds 1 and 2, and here is the observer. He will find that PPL is coming in the same direction, there is no rotation. Okay, so this such mixture of 1 and 2 is called racemic mixture. So if I say racemic mixture, it is equimolar mixture of two enantiomers are called as racemic mixture. Clear? Means a pair of optically active compounds which bear mirror image relationship when taken 50% composition of each. Such mixture is called as racemic mixture. Okay, mixture simply means there will be two compounds. Okay, here we straightforward means two compounds only, one compound and the other will be mirror image. Okay, and their equimolar mixture. Clear? Let's see the example. FClBrI. Suppose this compound we have, okay, this is optically active compound, and if I see its mirror image, what will happen? Cl and iodine will be same. This Br and F interchanges. So this is 1 and 2. If I say a container containing 1 plus 2, both 50-50%, then this is called as racemic mixture. This is your 50%. Okay, so one will be also be 50%. Clear? Equimolar mixture of two enantiomers, they are enantiomers of each other, are called racemic mixture. Or a pair of optically active compounds, a pair which bear mirror image relationship when taken 50% composition of each. Such mixture is called racemic mixture. Clear to everyone? Okay, now let's understand why it is optically inactive. Racemic mixture will be optically inactive. Let's understand this. FCl Bri, we have mirror image FBr as it is, but Cl comes here, iodine comes here. Let's check everything. It is having one chiral center, optically active. If I see simply if I see RS configuration, it is anti-clockwise, so S it is having clockwise, so it is R. Now RS won't confirm that PPL rotation will be clockwise or anti-clockwise, but if I say compound number 1 and 2, so what will happen? If 1 rotates PPL clockwise, 2 will rotate anti-clockwise. Okay, rotation of PPL, clear, and equal magnitude. So due to external compensation means the amount of rotation caused by compound 1 is compensated or balanced by the amount of rotation caused by second in equal but opposite direction. Okay, clear? Equal but opposite direction PPL is rotated, that is due to external compensation. Racemic mixture is optically inactive. Okay, clear to everyone? Let's take an example. If I say this compound, this is optically active, okay, but if I draw its mirror image, second, so I can say 1 optically active, 2 optically active, equimolar mixture of 1 and 2 optically inactive. Why? Because if the net rotation through this molecule will be angle theta, then the net rotation through this molecule will also be angle theta, but in reverse direction, opposite direction. Okay, for an example, PPL comes and passes through molecule 1, light rotates by 30-degree angle clockwise. Now it passes through this, light rotates in 30-degree but anti-clockwise. Now here is the observer, he observed that there is no rotation at all. Clear? So simply we can say that racemic mixture here PPL enters equimolar, PPL comes out as it entered, no rotation observed. Okay, clear everyone? So I think all of you must have understood what is racemic mixture. Clear? Okay. Representation of racemic mixture. Okay, now let's see how to represent a racemic mixture. Suppose you are given about 2-chlorobutane. So if you have 50-50% of both the enantiomeric pair, okay, then let's see first. 2-chlorobutane means CH3, CH2, CH, Cl, CH3. So this is 1, 2, 3, 4. 2-chlorobutane. See, this is having one chiral center. Okay. So suppose I have to draw see, due to this one chiral center, this compound is having some optical rotation, or for a particular concentration and all the entities, it is having a particular specific rotation. Okay. Now, suppose that a specific rotation for this will be theta, then its mirror image CH3, H, Cl, CH2, CH3. We can say the specific rotation due to this compound is theta, then it will be having a specific rotation minus theta. Okay. And if we are having equimolar proportion of these two, then net result will be 0 due to external compensation. Hence, for 2-chlorobutane having racemic mixture, you can represent it like okay. So students, remember this thing. If you are told that in a container we are having plus minus 2-chlorobutane or DL2-chlorobutane, generally it is represented by plus minus, but suppose you are told a DL, it also means the same. Plus is for dextrorotatory, means clockwise rotation of PPL, and minus is for anti-clockwise rotation, that is levorotatory. So if you are said plus minus 2-chlorobutane, it simply means you are having equimolar mixture of both, means there is an enantiomeric mixture. Okay, that will be 50% of one enantiomer and 50% of other. Clear? So the net rotation due to that part will be 0. Okay. So representation of racemic mixture is done like this only. Before that optically active compound, just write down plus and minus symbol both together. Okay. Let's see a question. Find the optical rotation due to enantiomer of R (3-chlorohexane) having specific rotation plus x degree. Okay. So students, let's see. If you are said you have to find the optical rotation due to enantiomer of R3-chlorohexane. So first of all, let's make 3-chlorohexane. See, 1, 2, 3, 4, 5, 6. Now third position is having chloro. So you can see here this part is having ethyl, this part is having propyl, this is having chlorine, and this is having hydrogen. Okay, so this is 3-chlorohexane. Now I have to draw the R configuration first of all. It is CH2, CH3. It is CH2, CH2, CH3. Now let's understand, one side will be having hydrogen, other side will be having chlorine. Now first of all I have to draw the compound R3-chlorohexane. So if I place chlorine here, then from chlorine towards this part it will be anti-clockwise, but hydrogen will be here, so it will be clockwise, means R. So let's place chlorine here. Now you can see 1, 2, 4, 3, right? So this is third. So as per the numbering, I can say it is anti-clockwise, so configuration can be S, but hydrogen in horizontal, so it is R. Now first I have drawn R3-chlorohexane. Now its enantiomer, means its mirror image. What will be its mirror image? it is EtCl this side, hydrogen this side, this is propyl. So you will be having optical rotation here S, right? So this is your S3-chlorohexane. Clear? Now if this is having optical rotation theta, it will be having minus theta. So as per given data, this is having plus x degree. Okay, so this will be having minus x degree. So this is your answer. Simply we can say theoretically without representing this all, but I explained you in order to show how to make such structures. See, from IUPAC name, now RS configuration is used in IUPAC naming, okay, to represent that this 3-chlorohexane, it is having one chiral center which is having configuration R. It is represented like this. Clear? Okay. Again, let's take an example of tartaric acid. Okay. Now, I can draw its mirror image. Let's see. If I place mirror here, the compound formed will be COH as it is. This OH comes this side, OH comes this side, H, COH. Clear? Now, another possibility of tartaric acid is if both OH are in opposite sides. So this OH, H, OH, H, COH and COH. Now again, placing the mirror, let me draw its mirror image. Okay. This OH comes this side and this OH comes this side. Clear? Now let me give it number 1, 2, 3, 4. Now let's understand all the points which we have studied till date one by one. First of all, you have to find out RS configuration. So simply this OH is 1, this carbon, oxygen, hydrogen, carbon, this carbon having 3 oxygen, double bond and single, those 2, NT, reverse, this is your R, this 1, 2, reverse, this is your S configuration. Clear? Now check, as this is the mirror image, I can surely say this is having configuration S and this is having configuration R. Let me check. OH towards COH, clockwise, but hydrogen in horizontal, reverse, anti-clockwise, S, 1, 2, reverse, R. Okay, perfect. Now check this one. OH means 1, COH 2, clockwise, reverse, this is S, and this one, 1 towards 2, clockwise, reverse, anti-clockwise. Now this is SS configuration, okay. Obviously, this OH was having S and this OH on this interchange, single interchange, S. Now you can see mirror image will form RR. Simply, you can check it. 1, 2, anti-clockwise, hydrogen horizontal, clockwise, R, OH, anti, reverse, R. Okay. Now RS configuration is over. Second point, optical activity. This is your having POS. So this is your optically inactive. This is having your plane of symmetry. Okay. Now this part, this is also optically inactive. Okay. Now check this one. No POS, no CS. Optically active. This will be also optically active. Okay. Now let me check a few more points. Relationship between 1 and 2. Yes. First of all, if I see 1 and 2, see, if the compound is optically inactive, means they do not bear mirror image relationship as enantiomer, then we can say the mirror image will also be identical. How? So let's see. I am telling the mirror image of this compound means 1 and 2, they are identical. Now when I say identical, I need to prove it. Okay, so let's do one thing. I can do, see, I have told you the properties of Fisher projection, right? So let's check it here. If I hold this part and I rotate in the plane of paper 180 degree, means this part towards this side and this part towards this side, 180 degree. So this COH comes here, this COH comes downside, this will go upside, this will go downside, and these two OH will come this side. See, this part on rotation in the plane of paper 180 degree, it will superimpose in this. All the atoms will coincide in this one. So I can simply say that 1 and 2 are identical. Clear to everyone? Okay. Okay. Now, when I say 1 and 2 are identical, then if I check 3 and 4, 3 and 4, they are mirror image and optically active, means they are enantiomer. Okay. Now check 1 and 3. 1 and 3, neither mirror image, non-superposable, means they are diastereomer. If I say 1 with 4, they are also diastereomer, 1 and 4. Okay. Now if I check 2 and 3, they are also diastereomer. Why? Non-mirror image, non-superposable. If I check 2 with 4, they are also diastereomer. Clear to everyone? So I have mentioned you 1 2, 1 3, 1 4, 2 3, 2 4 and 3 4. All 6 possibilities. Clear? Okay. Done? Okay. So let's check one more case. See, in this question, if I see one question arises, the question is, I have told you earlier, if any carbon is having chiral center, then PPL must rotate through that chiral center. Okay, means there will be optical activity through every chiral center. So what happens that in this case it is optically inactive, means there is no PPL rotation through this compound. So what happens actually in this compound? Let's study it in detail. See, in this compound we have two chiral centers. Okay, I am marking here this as one chiral center and this as another chiral center. Clear? Now if I check from this carbon, we are having 4 different groups. So there must be some amount of light rotation, PPL rotation through every chiral center. Clear? If I see the optical rotation through this one, OH towards COH, this is anti-clockwise but hydrogen in horizontal, so clockwise, this is R. Okay, suppose I make numbering, so 2R. Now let's check 3s. This is clockwise, reverse, this is 3s. So from carbon number 2, the configuration is R. From carbon number 3, the configuration is S. So what happens here is, from carbon number 2, if PPL comes and rotates through suppose angle theta, then I can see through carbon number 3, the PPL rotation will also be same in magnitude. Okay, but the direction will be changed because this entire group and this entire group are same, but configuration is different. So in this case what happens, PPL rotation through carbon number 2 and carbon number 3 will be same in magnitude but different in direction. So what will happen? The net rotation of PPL will be 0. So there will be no observation of PPL rotation. But in reality, there is having internally that rotation of light, PPL rotation. Okay, plane polarized light is rotated in equal direction in both sides. So net rotation is 0. Okay, clear? Now this is called as internal compensation. What happened? From 2, light rotated theta, then same rotated anti-clockwise theta and internally compensated, okay, means the rotation through one part is balanced or counterbalanced by another part and net rotation is zero. Such compounds are called meso compounds. Clear? Now, what is this meso compounds? Let me define. Compounds having two or more chiral centers but are optically inactive due to internal compensation. Okay, so meso compounds are those compounds which are optically inactive although they have two or more chiral centers. So such compounds are optically inactive due to internal compensation. Okay, PPL rotation occurs through every chiral center. Now one more point, but due to internal compensation they are optically inactive. So this is your meso compound. Clear to everyone? Okay, so let's check a few examples of meso compounds. Now this is simply 1,3-dimethyl cyclohexane. Okay, now what are the possibilities for this compound? I am just making an observation. See, if I check both the methyl in wedge or both the methyl in dash, see, I have drawn four possible cases. Okay, if I'll check in these all, see, if this, suppose for cyclohexane I have already told you, assume it as a rigid. So you can see, if I take the plane from this part, so it is having plane of symmetry. Although this part is your chiral center and this is also your chiral center. So you can see your number of chiral center equals to 2, but it is having plane of symmetry. So this compound is your meso compound. Now, if it is meso compound, then it is also optically inactive. So these two are actually identical. If I observe from this side, these two are towards me. But if I observe from back side, these two will be observed as away from me. Clear? Number of chiral center equals to 2 in all four cases. These two are optically inactive. If I check this one, 2 chiral center in both, but they are not optically inactive. They are optically active. Okay, so we have discussed in this lecture about properties of Fischer projection, about diastereomer and about meso compounds. Remaining we will continue in our next lecture. Okay.